This is a continuation of the discussion regarding energy from the first lecture of week 2. This is the second lecture. Energy, as I talked about earlier, can be transformed from one form to another. In Physics 1, we talked about transferring it from kinetic energy to potential, back to kinetic energy. And there's, of course, different forms of potential energy that we talked about. You have chemical potential energy and even nuclear potential energy, where energy is wrapped up in the actual atomic structure. And we're primarily concerned with, in this class at the moment, electrical energy and mechanical energy and transferring between them. So we can get a motor to run from hooking it up to a battery. That's an example of that. And the fact that you get some loss typically when you're transferring from one to another in the form of heat. And also the concept of what is a system. Usually we're transferring energy maybe from one system to another. So where are our systems? Where do they come? How do we define them? And I might think of as a motor as a system, and electrical energy as something coming in from a battery, from another system to that motor. And as I mentioned earlier, you can't create or destroy energy. It can be transformed, converted, but it never comes from nowhere and never goes nowhere. It can dissipate as heat, but it hasn't gone anywhere new or different other than embedded into the vibrations of the molecules that are in the air. So when we say we're using energy, we're actually converting it from one form to another. That's what's meant by energy use. An example of that is, for instance, these are those little solar night lights. So you get energy coming from the sun that is being used, or in this case, it's being converted to store energy into a battery that can then at night, there's a little detector that says, oh, it's dark outside. I'm going to turn the switch of the battery on and I'll light a light. So the energy from the sun is being converted to chemical energy that's stored in a battery that's later converted back to electrical energy that goes to lighting the light bulb. And that's what's described below. Or in this case, not a light bulb, but a light-emitting diode. And as I mentioned, energy efficiency, and any sort of efficiency, is a relationship between what you get out on the bottom versus what you had to put in on top. So energy efficiency energy efficiency is what you get on top divided by what you had to put in. That's on the bottom, what you had to pay. As a reminder, the concept of efficiency relates to how much you get versus what you put in to get what you're trying to get. So in other words, if you put $10 in towards something and you get $9 out, that would mean an efficiency of 90%. Now with efficiency in physics, you can never get out more than what you put in, and you'll never even get out what you put in as far as energy goes. So if you put so much energy into something, you get a little bit less out. If you get more out, then it's coming from somewhere else. So that's the idea about conservation that enters this. And the missing energy, of course, becomes heat. Typically, that's how it goes away, or seems to go away. It becomes something that's less usable. So an efficiency can be applied to things other than energy, but it's often applied to the concept of energy. So it relates, again, what you get out divided by what you had to put in, and it can never be greater than 100%. So here's an example where we can think about energy. 15-watt LED bulb and a 75-watt incandescent bulb each produce 3 watts of visible light energy. So watts is a unit of power, not a unit of energy. But it tells you how much energy. Sometimes the words get used a little bit interchangeably, but a watt tells you how much energy is produced every second. So 15 joules per second go into an LED bulb, 75 joules per second go into an incandescent light bulb. both of them produce 3 watts of joules per second of light energy. The rest goes to heat. So calculate what the efficiencies are for each of these bulbs. And where did the rest of the energy go? And if you look at the calculation for the LED bulb, the one on the left, 3 watts is what you get out, divided by 15 watts, which is what you put in, that gives you 0.2 or 20%. Similarly, 3 watts divided by 75 watts is 3 joules per second divided by 75 joules per second, and that gives you 4%. So it's a much lower efficiency. And while these seem low, it's pretty typical for light bulbs. A lot of the energy of light bulbs goes to heat. That's where the missing energy is going. And the energy we get from our houses, keep in mind that typically comes from some sort of a power plant, which is trying to convert heat into motion, from which it creates electrical energy in ways that we'll talk about later this semester. But this little cartoon gives you an idea of what's going on, where you have water coming in that's then heated, and from, let's say, fuel, let's say it could be from nuclear fuel, it could be from burning it with coal, burning it with natural gas that's on fire, that's lit, and that's where the heat comes in. So a lot of that heat goes into heating the water, but a lot of it is also lost. That hot water then is in the process of it going converted to steam and then cooling back down. It drives a turbine. It actually can push a turbine, cause it to turn, from which we can get energy. And that whole process is maybe at best 30 to 35% efficient. So most of the energy that's being produced by burning fuel to create the heat in the first place is dissipated as heat. It's kind of like it's lost. It's not really lost, as we said, it's converted to heat, but effectively it's lost as far as the ability to produce electrical energy that we're trying to do in the first place. In some cases we can use that heat to do things, but essentially it's lost from this perspective here. And here's some examples of efficiencies of different parts of transitions from one type of energy to another. And as you can see, for most power plants, the best you're going to get is about 40%. And of course, when you look down here, you'll see solar looks really low. That's because we only convert a small percentage of the energy that's in light to electricity using solar cells. But that's okay, because we're not the ones creating the sun, causing it to burn. We're just catching a small fraction of that energy. So even though solar has low efficiency, it's not like we're burning something in order to create that. And so we're not losing energy that we burn something to create. That's happening up in the sun, not something we have control over. And if you multiply all of the different efficiencies from all the processes that allow us to get energy at our houses, from the burning of whatever at the power plant, let's say that's 35% efficient, you send that electricity across using transmission lines, you lose a little bit of energy on transmission lines. They get a little warm, for instance, and then that energy from the transmission lines is converted down to your house and used in a light that might only be 5% efficient if you're not using an LED. That means the overall efficiency of lighting a light bulb from energy taken from a power plant is about 1.6%, which just seems so problematic to me. You're getting not even 2% of the energy that you're burning. It's like, wow, where's it all going? Well, a lot of it's going to heat. And it's unfortunate, but are there ways we can find to be more efficient? And there are. And we'll talk a little bit about some of those in the next video.